Hello again. So in this lesson, this is the first lesson after the introduction. So in this lesson, we are going to look at how to apply finite element method to solve steady state diffusion equation in one dimension. Since this is an intermediate level course, like you are expected to have some fundamental knowledge of the finite element method. Okay, if you are not familiar with that, I would suggest you go to any resource on finite element method, especially programming finite element method for simple problems, like even 1D problems is sufficient enough. And if you don't have any good resource, so like you can follow my videos on YouTube. So I have already created some videos on implementing the finite element method for some 1D problems as well as 2D problems for simple problems. Okay, so and there is a link to this video in the description of this, okay, of this video. So like if you need to brush up your knowledge of programming in MATLAB and also are active and programming for finite element method, please go to that video and follow it and come back to this video. If you already know how to do it, then skip it and continue with this video. Right. So first we are going to look at the diffusion equation with homogeneous Dirichlet boundary condition. Homogeneous Dirichlet boundary condition means the boundary conditions are zero. Okay, so we have in one dimension the governing PDE is given as this. So we have mu dou square u by dou h square. Okay, so minus of mu dou square u by dou h square equal to f. Okay, so here mu is the material parameter. For example, like since we are solving diffusion equation, this is a diffusion coefficient. U is our solution variable and f is the source term. And let us say that our domain in one dimension spans from HL to HR. Okay, so this is our coordinate is x, and on the left hand side we have the x coordinate as HL, on the right hand side we have the x coordinate as HR. So the domain is from HL to HR. Okay, and on both sides, on both ends, the solution is specified and it is zero. So that is why this is a homogeneous Dirichlet boundary problem. Okay, so on both sides we have the solution at zero, and these boundaries, these two boundaries, we denote them as Dirichlet boundary. Okay, so when we say Dirichlet boundary, we mean that there is a specified value of the solution on those boundaries. Okay, so in this case, the Dirichlet boundary is in the union of the left end and the right end. Okay, now, so since you already have some basic knowledge of the finite element method, I'm going to like go through the fundamentals where whenever we need them, go through. I will go through them in a quick fashion. So okay, but of course slow enough for you to follow. Okay, now the first step in the finite element method is to derive the weight form. Okay, so to derive the weight form, we start with the residual of the PDE. Right, okay, so we have the residue of the PDE, and then we use the weighted residual statement, that is the integral of the dot product of the weight function W and the residual of the PDE, that is the integral over the whole domain should be equal to 0. Okay, so the dot product of the weight function W and the residual R integrated over the whole domain, that should be equal to 0. Here we have that it doesn't make much of sense to use the dot product because both W, the weight function, or the residual of the PD are scalars. But when we go to vector field problems, dot product becomes important. So in this case, we can ignore the dot product. That dot product becomes just the scalar product. Okay, and then we use the residual, that is minus mu dou square by dou square minus f into the weighted residual statement, and then we split the integral. We take f to the right hand side. We are given f, so we keep it to the right hand side. Now the left hand side we have the integral of w. mu dou square by dou h square. And of course, there is a minus. Okay. Now, here, if you notice carefully, on u, there is a second derivative, which comes directly from the PDE. If we were to solve this equation, if we were to discretize this equation, we need the solution field such that it not only the solution but also the first derivative is continuous across the elements. So which is a much stronger requirement, and it is difficult to have such basis functions. Of course we can have, but it is difficult to have, and they come with some challenges. So in order to overcome these challenges, so what we do, we transfer one derivative from u to w. By doing that, we are weakening the derivative requirements and the basis functions. So in this regard, the final form that we get is called weak form, since we are weakening the derivative. Okay. Okay. So in order to transfer the derivative to w. So what we do is we use the derivative of product rule. So this is right. Okay. So if you have two functions and if you take the derivative, then we have, like for example, so here w and dou u by dou x are the two functions, and we are taking the product and derivative of the product of w and dou u by dou x. So we take the derivative of w and then dou u by dou x remains constant plus w times the derivative of dou u by dou x. Okay. So this is uh, something we learn in high school. Okay. Now in this expression, so I'm going to just place this assuming that mu is a constant, we can like multiply both sides by mu, and then we can insert mu into this derivative of product rule. Okay. Now what we need in the integral, okay, so in this integral we need this w mu dou square by dou square, which is what we have here. Now from this equation we calculate this w mu dou square by dou square, and then take this entire term by taking this to the left hand side, to the right hand side, and then substitute here, and then after modification we have, okay, so we have minus here, we take it to the left hand side, we get minus minus plus, so okay, plus mu dou u by dou w by dou x and dou u by dou x dx, and this term remains as it is on the left hand side, and since it is minus, so we have minus here. Okay, and on the right hand side, this wf dx it remains. Okay, so this is the intermediate step in deriving the weak form. We still haven't applied the boundary conditions. Okay, now next what we do, you make use of the divergence theorem to apply the boundary conditions. We know the divergence theorem. Okay, so according to divergence theorem, the volume integral of divergence of a vector field is equal to the surface integral of the vector field and its dot product with the normal, outward pointing normal. Okay, so for a one-dimensional integral, okay, we have only one component of f. Okay, so that is the fx. Okay, so dot product becomes dou by dou x of fx. So that integral becomes just the integrated value. Okay, so that here f dot n, so only fx and x, and then we apply the limits. These are the boundaries, right? Epsilon and epsilon. Okay, so our fx is this term inside the bracket. So by comparing this with this, we can apply the divergence theorem to this term. Okay, we have fx and x and then the limits. Next, we split the limits. Okay, so upper limit and lower limit. Okay, so for the upper limit we have minus, and then for the lower limit we get another minus, so minus minus plus. Okay, this is the term. And then we also know the outward point and normals at both ends of the domain. So at the right end, the outward point in normal has a value of +1, and at the left end, it has a value of -1. So we can substitute those values. Okay, we don't simplify it. Okay, so we start from after we substitute the normals, and then so we have two terms here. So one is W, the test function, and then this product of mu and dou by dou x. Okay, so we split in the sense, so we apply this to both terms separately. Okay, so that is we evaluate W and we evaluate mu dou by dou x at x equal to xr. Similarly, for x equal to xr. Okay, now we use the boundary condition. Now we know that we have two homogeneous resistor boundary conditions at both ends. Now, in order for our solution to satisfy this, we need to choose a test function W, the test function W, such that it is in the H10 space. Okay, so H10 space is the space of functions where the function is square integrable. Okay, uh, where the function and its derivative are in L2 space. L2 space is a square integrable space. Okay, space of functions. Okay, right. Okay. And H10 means it, like, in addition to being in the H1 space, W vanishes on the Dirichlet boundary. That is where the solution vanishes. So by choosing the weight function such that it is in H10 space, what we can do is, since it vanishes on the boundary, and these are the boundaries, these two terms become 0. Okay, so after applying the boundary conditions, we are left with only two terms, one term on the left side and one term on the right side. Now this is our weight form. So this weight form is stated like this. So for all weight functions in H10 space, find u in H10 space such that this weight form is satisfied. Okay, so this is the weight form. This is the first step in applying the finite element method. After we have the weight form, we apply the discretization. We discretize the domain, or we approximate the domain. Okay, before we discretize, first we approximate the solution. Okay, so approximation using a linear combination of basis functions and the degrees of freedom. So let us say in general we have n degrees of freedom associated with their respective n basis functions. Okay, and this is the linear combination, and we can represent it in matrix vector form. Like here, bold face n is the matrix of basis functions, and bold face u is the vector of degrees of freedom. And note, we know that only n depends on the coordinate, so we calculate the derivative of u. We have dou bold n by dou x, and then the vector of degrees of freedom. Similarly, by using the Delaunay method, we approximate the weight function, and because of the Delaunay method, the basis functions for the weight test function are also the same as the basis functions for the solution. Okay, and for the weight function, we also represent using the transpose. Okay, so W equal to N W in vector form, and we can, by taking transpose, we can also write like this. So W transpose multiplied by N transpose, and then we have the derivatives. Okay, now after taking the approximation, we can apply these, like we can use dou u by dou x equal to this and dou w by dou x equal to this into the weight form expression, and w equal to w transpose into this right hand side. Okay, and then so we can write like this. So our mu is here. So for dou w by dou x, we have w transpose dou n by dou x whole transpose. Okay, and for dou u by dou x, we have dou n by dou x multiplied by u. Okay, similarly for w, we have w transpose and transpose, and then we notice that for any arbitrary w, this equation should satisfy, and this is our ku equal to f. Okay, so this is the term on the left side inside the bracket is our stiffness matrix, and U is the vector of degrees of freedom, and on the right side it is the force vector. Okay, this is the discretized form. We still haven't split the domain into finite elements. With that we do next time, right? In the next step. Okay, so we have discretized. We don't know how many elements are there. Okay, and we don't even know that we have split the domain into a number of elements, because here at this point it is still the integral over the whole domain. Okay, we know that we have like n basis functions and n degrees of freedom. Okay, if we evaluate this integral, we will have an n by n matrix. Okay, so as you might already know, in finite element method, in order to simplify the task of evaluating these integrals over the whole domain, we split the domain into like a number of elements. So that is where we get the concept of elements. Okay, now so we have the discretized form, and once we split the domain into a number of elements, for example, let's say 4 elements, that would be more number of elements. Okay. Then for each element, okay, so for a two noded element, we can calculate, or for any noded element, for each element, we calculate the element stiffness matrix by limiting the integral to within that element. For example, if we take the first element, okay, so it is from x1 to x2, and then we calculate the respective basis functions and integrate them. Similarly for the force vector. Now, by by taking a master element, okay, master element with nodes 1 and 2, and then the basis functions n1 and 2, okay, we know we can derive their basis functions, and then we can calculate the partial derivative of the basis functions, and after using these derivatives into this expression and integrated these expressions from x1 to x2, we get this 2 by 2 matrix. So this is for a 2 noded element, and each node has 1 degree of freedom, which is the diffusion variable u. Okay, so u1, u2. So the matrix is of size 2 by 2, and this is the closed form expression for the element stiffness matrix. Again, the matrix is very like is exactly the same as what we use in the bar element. Here, U becomes our material property in the bar element EA. Okay. Okay. So yeah. So there is a lot of there are so many problems that we can solve using the same formulation just by changing the physical meaning of the parameter. Okay. So this is our stiffness matrix, and similarly we can derive the force vector by assuming that the source f small f is a constant. This expression is not valid when f depends on the coordinate x. Okay. So but for this lesson, it is sufficient if we assume that the source term f is a constant. Okay, if f is a constant, we get fh by 2 1 1. So what we are doing is basically, so we are multiplying the source term with the length of the element and then distributing it equally on both nodes. Okay, so off and off. Okay, so now in order to see how like we solve a problem using the finite element method, so let's take an example. So here again we have, this is our PDE, and here instead of some arbitrary or like domain limits at cell at R, we have a domain going from -1 to +1. Okay, and we take mu and f as 1 just to keep it simple, and our boundary conditions are both zeros. And for this problem, for these parameters and with these boundary conditions, we can derive the analytical solution, and it happens to be minus half x square plus half. Okay, it's like a parabola. We use this for our reference. Okay, so in order to solve this, we split the domain into like for 4 elements. Okay, our domain is from -1 to +1. We have 4 elements equally spaced. Okay, so we have 5 nodes. Okay, and this is our element node connectivity matrix. Okay, this is the node number, element number, and this is the first node, and this is the second node. So like these are the nodes, okay, for each element. Okay, so by using the fact that we have mu equal to 1, and since we split the domain into 4 elements, we have an element length of 0.5. 2 by 4 is 0.5. Okay, so from this we can calculate the element stiffness matrix, and f equal to 1, so we can calculate the element force vector. Okay, so this all of this you should be familiar in order to understand this course. Okay, again, if you don't follow this, please go back to the other video on implementing the FEM for 1D problems, because without understanding this, you will not be able to progress further. Okay, right. Okay, so and then once with this information, we need to calculate the global stiffness matrix, and since we have 5 nodes and each node has 1 degree of freedom each, so we have a 5 by 5 matrix. This is a global stiffness matrix. Now, okay, and then we have a force vector which is of size 5 by 1. In order to create or prepare the global stiffness matrix from individual element stiffness matrices, we use this table, this array, and we keep on adding the contributions from individual elements into the global stiffness matrix. So like I said, we have 5 nodes, so 5 degrees of freedom, so 5 by 5 matrix in the global system. And for the first element, so the 4 entries in the first element stiffness matrix, they go into first row, second row, and first column, second column, like this. And for second element, they go into row 2, column row 2 and row 3, column 2 and column 3. So like this. Similarly, for element 3, into rows 3, 4 and columns 3, 4. And for element 4, into rows 4, 5 and columns 4, 5. Okay. And similarly, we assemble the global force vector by adding the contributions from individual element force vectors. Okay, so the force vector is of size 5 by 1. So we have 5 entries, and this is from element 1, from element 2, from element 3, and from element 4. Okay, so whenever there is more than one dot in each cell, we add them. Okay, we add them similarly here. So we add the values of these 2 dots. So okay. So you should be able to assemble this by hand. Okay, so since we know this element stiffness matrix, okay, so 2 minus 2 minus 2, 2. Okay, so by following this analogy, this method of assembly, you should be able to calculate the global stiffness matrix. Okay, of course, we will implement it in MATLAB or in Octave. Okay, so once we assemble the element stiffness matrices for all the elements, so this is the global stiffness matrix we get. And as you notice, so in the diagonal, except for the first and last one, there is 4. So this diagonal gets 2 values, one from the left side element and another one from the right side element. So 2 plus 2, 4. Since we have a mesh of uniform element size, so the values would be the same. Values are the same. And similarly here. So 0.25, 0.25 for each element, and for internal nodes, okay, they did the contribution from both elements, okay, on the left side and the right side. So 0.25, 0.25, that would be 0.5 for all the internal nodes, 2, 3, and 4. Okay, so this is our global stiffness matrix, and this is our global force vector. Now we know for a fact that, okay, we know that the boundary conditions are zeros. Okay, so we eliminate the degrees of freedom. the first one and last one. That is, we remove the first row, last row, and first column and last column. So by doing that, we get a simplified or a reduced system of equations. Okay, so in U2, E3, U4, these are the values that we don't know. So, okay, so we solve for them. Okay, we find them by solving this 3 by 3 matrix, this 3 by 3 system. Okay, so once we solve for U2, U3, U4, we get the values. Okay, and then we can plot them and compare with the exact solution. Okay, so let's try to implement this in MATLAB in Octave. Okay, if you have MATLAB, you can use MATLAB. Okay, so there is not much difference between Octave and MATLAB. So I'm using Octave to encourage open source software tools. Okay, so just to help us, so I have the code like, but not completely done, but I have some inputs already prepared. Okay, so this is Excel, the left side x coordinate, right side x coordinate, the parameters mu and f. So we have four elements. NLM is the number of elements, N node is the number of nodes. Okay, HA is the length of the element. Since we are using uniform mesh, so the HA is the same for all the elements. And that we need the nodal coordinates. Okay, for purpose of plotting mostly. Okay, so I'm preparing the nodal coordinates for each node. So we know that there is only 1 degree of freedom for each node. Okay, so ND of is 1. So we know the number of nodes, and if you multiply it with n node n DYF, okay, so we get a total DYF, that is total degrees of freedom in this problem. Of course, total DYF is equal to n node because that n DYF is only 1, but it is a good practice to do this for future. Like when we solve problems like storage flow and Navier-Stokes, there we need like more than 1 degrees of freedom per node. So there it would be helpful. So it's better to cultivate this habit of like calculating the total degrees of freedom based on the number of nodes per node and number of nodes. Sorry, number of degrees of freedom per node and number of nodes. And this is an array which is useful. So DOF fits. So in this, I have 1 and total DOF. So this array has two values, 1 and total DOF. So like in our problem, okay, we have both. We know the values of node 1 and node 5 are total DOF end node fixed. So these are the fixed DOF. And once we know fixed DOF, we can calculate the free DOF, that is internal degrees of freedom, by taking set diff. Okay, we know the total degrees of freedom, so should be from 1 to like 5 in this case. So and if we subtract fixed DOF from the total set, we get free DOF. Okay, so we can have a look. Okay, so for example, so fixed DOF are 1 and 5. Okay, and if you do this, we get an array of 1, 2, 3, 4, 5. So by taking the difference of this array and fixed DOF, we get a device free array. Okay. So I'm doing in this fashion so we can generalize it to n number of elements. We can change the number of elements and it will take care of the device fits and device free arrays automatically. And this is the element node connectivity array. So this is this table, this array. Okay, again, I am creating it in this fashion so that it generalizes to arbitrary number of elements. If you change the number of elements, these arrays are populated automatically. So this next array is like the same as element node connectivity array, just the name difference. And again, like I mentioned here, this array is going to be useful, and this is what we use for assembly. Okay, if we have more than 1 degrees of freedom per node, then these two arrays would be different, and that would make a significant difference when we do the assembly. Okay, so we have the variables, we have set up Next, we are going to create a global stiffness matrix. Okay, it should be of size total DYF by total DYF, and then we need a global force vector should be of size total DYF comma 1, and then we need a solution array to store the solution. Okay, and then we loop over the elements. So element number 1 to n element. Okay, close the for loop. Okay, so for each element, we need to know what are the rows and columns into which we are assemble the elements stiffness matrix. Okay, so we get this from this array. Okay, so we extract all the columns of that array corresponding to the current element number, and the columns are equal to rows. Okay, next we calculate the elements stiffness matrix. Okay, so using this formula mu by he 1 minus 1 minus 1 1. Okay, mu by he 1 minus 1 minus 1 1, and Fe is FHE by 2 1 1, FHE by 2 1 1. Okay, so we assemble this into the rows and columns. Okay, and we add it to the previous values. Okay, similarly, the force vector. Okay, so this completes the assembly process. So this is the assembly into global quantities. Okay, so at this point we have K global and F global. Okay, so we can run the program and see. Okay, so as you can see, so we get this assembled matrix system 2 minus 2 minus 2 4 minus 2. Okay, so we can compare the values, and this is our global force vector. Next, we apply the boundary condition and solve for the unknowns. Okay, so we don't need to create any temporary variables. So what we can do, so we are solving for the unknown degrees of freedom, and what the solution we get, we place it in the solution vector at those corresponding degrees of freedom. So we extract the rows and columns corresponding to free degrees of freedom and solve the corresponding matrix system. Okay, so we are solving for free degrees of freedom. The free means unknown, that we don't know yet. Okay, so we solve here. Okay, as you can see, so the first one and last one are 0, we know them. Okay, in between we have 3 nodes for which we don't know, and after solving these are the values. Okay, next we plot the solution. Okay, so for plotting we use this node coordinates array, and then the solution. Okay, so let's use star. Okay, so this is our solution. For comparison, we use the unlimited solution minus half h squared plus half. Okay, hold on. So for plotting the unlimited solution, I'm going to use a smoother one. So I'm going to use more points. Okay, so I'm calling it as exact solution. So minus 0.5 star square plus 0.5. So plot x comma u exact. So I'm going to plot it as L9. Okay. So I'm using more points here just to get a feeling about the exact solution. Okay, so like I said, this is a parabola, and these stars are our FEM solution. Okay, we can also add a line if you want. Okay, so here we have a straight line. Okay, so we have only two nodal elements, so the solution is expressed by a straight line between the nodes. Okay, so as you can see, the solution matches pretty well. Okay, so in the other video, I show even I like how to plot the error. Okay, and okay, you can follow it from there. So now let's see what happens if we increase if we change the number of elements. So to 10. Okay, so as we change the number of elements, the solution gets closer and closer to the analytical solution. So this is mesh refinement. The solution should converge with mesh refinement. Okay, so if your solution doesn't match with the analytical solution, then there is a bug in your code. So this is it's always important to verify your implementation using the manufactured solution. Okay, so this is how we solve a PDE. Yes. In particular, this is how we solve the steady diffusion equation, where the boundary conditions are all zeros. Okay, so I'm stressing this because there is a it holds some importance, and the finite element method needs to be slightly modified for problems with non-homogeneous display boundary conditions. Okay, that's what we are going to look next. Okay, so with that, okay, we have implemented the first code for solving the 1D study diffusion equation using finite element method. So this code needs a little bit of tweaks to incorporate non-zero boundary conditions. So I'm going to do this in the next part. Okay, so same lecture but next part.